Now, in the next sections 4 to 8, I give you a 5-fold classification of experiments. Experiments can be classified in various respects, and although you do not understand now what I'm going to tell you exactly, I'm presenting 5 different classifications of experiments according to their distance to reality. I'm going to explain that. Then whether or not they have an explicit control experiment. Then what sort of purpose the experiment has. Is it testing versus exploration? Then there are intended versus natural experiments. And there are finally literal versus metaphorical experiments. And also this is an important distinction because sometimes in the literature you find some confusion. Now, mostly these classifications do not have very sharp or extremely sharp boundaries. There are overlapping areas, transition areas, but that doesn't make the distinction and classification useless. So let's start with the first classification, which is, I think, also almost the most important one, namely what I call what distance of reality they have. And I claim that experiments can have very different sort of distances between experiment and reality. And the first is whether the system that is experimented on and the system one is really interested in. That is what I mean by the distance of reality. And of course, because these two systems don't have to be identical, and the larger the distance between these two systems is, the larger is this distance to reality. And I'm going to distinguish between 5 possibilities ranging from no distance to a very large distance. And this is what I'm going to discuss now, namely field experiments, laboratory experiments on the system of interest itself, laboratory experiments on surrogate systems, computer experiments, and thought experiments. And the idea is then that the distance to reality increases here from 0 to, well, infinity, well, to a very large distance of the thought experiment to reality. So let's start with the field experiments. Field experiments have become very important in economics. And the main idea, or the fundamental idea of a field experiment, is that you make an experiment of the intended system of interest itself in its own, so to speak, natural environment. That's a field experiment. Natural environment is ambiguous. In biology, of course, it means if you experiment on animals, then you don't experiment on zoo animals, but you experiment on them in their natural environment. And in economics, of course, what is called here natural environment is that what is naturally occurring. So when you speak about a school in some region of Africa, then you mean you make the experiment in a field experiment on schools of that region in Africa. So, for instance, school experiment. And this is a real case here. You have the question whether in a certain region in Africa, does a free lunch offer increase the school attendance of pupils in a certain region? And this is really a field experiment that has been carried out. Well, this is a very simplified version I'm discussing at the moment here. See later subsection 5 for more complicated cases. And what you do in this field experiment is you offer free lunch in certain schools in that region and observe whether school attendance changes. And that's, of course, an experimental setup. Now, field experiments have become important in many fields of economics, especially in developmental economics, where this seems to be now the gold standard. And there has been a Nobel Memorial Prize in Economic Science 2019 for such research based mainly on field experiments. Banerjee, Duflo, and Kramer got the Nobel for their experimental approach to alleviating global poverty. And these were mainly field experiments, plus, of course, theory that were carried out by these people. Now, in field experiments, it's, of course, first the question of internal validity that arises, namely, do I get reproducible results for the investigated cases? This is obvious. For real-world applications of these results, then often the generalization to other cases is necessary. For instance, if you apply what you learned in one region, say in Africa, and you try to apply to other geographical regions, then it's the question of external validity. And it's not trivial that a result that holds in one region may also hold in another region, because in the other cases, you may have different economics conditions or different cultural conditions or whatnot. So the results of your field experiment, the internal validity, may be dependent on certain parameters that you kept, possibly without knowing, constant in your field experiment. These parameters may take on different values when you go to a different region, and then your result may not be longer be valid at all. So there is a question again of the transition from internal validity to external validity in field experiments. Now, the next kind of experiments that I want to discuss, and these are the most common ones, well, not really the most common ones, 4.2 and 4.3 are the most common ones, is in general laboratory experiments. And the laboratory experiments can be carried out on the intended system, and you have to bring in the intended system into the laboratory in order to experiment on it. That is sometimes possible and sometimes, of course, not possible. The main advantage of the laboratory experiment in comparison to mere observation or in comparison to the field experiment is that you have better control. So you have better control of the environment of the system, and you can set up in these experiments that you can bring into the lab, you can set up the environment and keep it constant in order to keep the influence of the environment constant on the system. Because you want to know what happens when I change certain variables and what is their influence, their causal influence on the system. And therefore, you have to keep all the other possible causal influences on the system constant. And this is, of course, much easier in a laboratory situation, in many situations at least, than in the field. So this is the first part of the higher control that you have in a lab experiment. The other one is you have a better control of the intervention on the system. And the intervention in the lab on the system can be better planned and controlled, such that it can be better, possibly quantitatively correlated with its effects on the system. So the point simply is, if you bring the system into the lab, your possibilities of control are much higher than in the field. And to give you a very simple example from physics that you probably also heard in high school already, you want to investigate the ideal gas law. P times V is constant, P is the pressure, and V is the volume. And then what you do in the lab, you take a sample of the gas, you hold the temperature in the lab constant, because you know that may be temperature dependent, and it is in fact, and then you vary the volume of your gas sample stepwise, and you measure the correlated pressure. And all that can be done with laboratory equipment, and you keep all the environment constant, and then you get the influence of the variation of volume on the pressure. And if you have the right gas and the right conditions, then you may get the result that T times V is constant in the cases that you investigated. If you look at another example, namely, say, a genetic experiment in the laboratory on Drosophila melanogaster, that's a fly, that's a fruit fly, and this is one of the pet animals in biology on which many experiments have been made. And then you make a genetic experiment on that species, on the specimens of that species, and that's then an in vivo experiment on the intended system. Drosophila is often called a model organism, and I want to say some words on that because that's also an ambiguous denomination. In the given context, a model organism does not mean a model of an organism, but a real organism that has an exemplary character. So I'm going to show you later that also a different meaning of model organism can be in play. In this particular case, it just means the organism has an exemplary character, and this is all. Now, in that particular situation, then primary questions of internal validity arise because internal validity already concerns the system you're interested in. That's very important. However, if the interest is not only in this particular species, say in the biological case, so you find something about the genetics of Drosophila, but you are interested not only in Drosophila genetics, but more generally in questions of genetics, then you want to generalize to other species. And then, of course, questions of external validity arise. So it depends on your questions that you want to answer by the experiment, whether questions of external validity come up as well. Usually in biology, for instance, that is the case, but not always. So the third kind of experiments that I want to discuss, and that is different with respect to the distance of the experiment to reality, is when you carry out a laboratory experiment, but not on the system itself that you're interested in, but on a surrogate system. And that may have, of course, a very, very obvious reason that for some reason you cannot experiment on the original system. So you say, I want to have experimental data on that system, but I experiment on a surrogate system. Okay, so of course, such laboratory experiments, not on the intended system itself, but on a system, on a different system, have to experiment that is somehow, whatever that means precisely, sufficiently similar to the original system, on the surrogate system, as I will call it. And that sort of similarity, of course, comes in degrees, and that's also important for economics. And I give you a few examples here. Now, first from technology and the natural sciences. Imagine you want to know what the airflow around a real car is. Because you want to optimize the resistance properties of your design of that car, and then you want to know what the airflow is. Usually this is done, or very often this is done, by an airflow measurement around the real car, while not the same material perhaps, but exactly the form you are interested in the wind channel. Now, this is already a surrogate system, because in reality, the real car is moving through stationary air, and this is replaced by a stationary car and flowing air. Now, physics gives you an argument that these two different situations are, as far as the physics are concerned, mostly equivalent because of the relativity of the coordinate systems. In that case, that's not so important. The point is still, you replace the original system by a surrogate system. In this particular case, you have a very good argument from physics that tells you information that you gain about the surrogate system is really information that's valid for the original system as well. Here's a modification of that experiment, and that leads you further away from the original system. It's an airflow measurement around a downscaled model of a car, which is of course cheaper, and therefore you want to do it. Or, for instance, you want to have the properties how a ship moves through the water, and then because some of the ships are rather large and too large to bring them into a lab, you make an experiment on a downscaled ship, and then you look how does the water flow around the downscaled ship. Now, this is a situation which is more complicated, and also physics tells you under which circumstances a downscaled experiment gives you information about the original situation. Now, here's the next example from biology. Imagine now a genetic experiment on Drosophila, but you do not experiment on the living organism, but you have a cell extract of Drosophila in which you put all the ingredients you think that are important, and then you run the experiment, and this is then a typical in vitro experiment in which not the living organism is the object of the experiment, but it's some part of it, but certainly not the living organism. Or take experiments, example 4, pharmacological experiments in human medicine using mice or other animals. These are very, very, very common that in the first phase of experimenting, on living beings in pharmacology and medicine is experiments on animals. Human mice, mice are a very good example for that. And then somehow one hopes to get information about the real system, although one works on a surrogate system. And this is now the other situation I was already implicitly referring to, because also in this situation, a mouse may be called a model organism for humans. And now it's meant as a model for a human body in the sense it's a replacement of the human body. So you experiment on a mouse. The mouse is a replacement for the human, for a human organism. And also that is called a model organism then, but that's of course a different meaning. In early behavioral economics, experiments usually belonged to this kind, to this third kind, where you make lab experiments on a surrogate system, and then you try to extrapolate to the real situation. And there were in very early experimental economics in the 50s, they were very remote from reality. And a typical choice question was then, for instance, imagine you have the choice between the following lotteries. How would you decide? So this is an example from Allais from 1953, and many similar examples are in Kahneman and Tversky in their famous paper on prospect theory. So the sort of experiment is really an experiment of kinds, of sorts, because you have to imagine you have to choose between lotteries, and then you give the answer how you would choose in that imagined situation. And of course, this is a sort of experiment, and then the question, of course, arises whether that is information that's useful or is not. So a real choice is replaced by an imagined choice, and that may or may not make a difference. Certainly, it was highly controversial in the beginning whether results from imagined choices can be transferred, extrapolated to real choices. In addition, and that's still today, this is a very tricky situation, not only in economics, but also in psychology and other disciplines. Human subjects were mostly college students and not people, for instance, in economics, who are active in the economy. Of course, sometimes you make experiments also on people who are really active in the economy. You bring them to the lab and run an experiment, but mostly because it's, of course, obviously easiest for university professors to recruit college students and to run the experiments on that. But again, one has to see this is a surrogate system. It's not the original system, and therefore questions of external validity arise. Of course, the trend was, which is quite obvious, that experiments became more realistic in time. And now the standards is really that you have real choices, and the incentives are not imagined incentives, but they're real money incentives. They're still often carried out on students. And for the money incentives, you sometimes go even to countries such that the money incentive can be something like a monthly wage, that you can really test whether people, when it comes to money incentives that are really real for them, whether they behave in the way that the experimenter wants to investigate. So for instance, in public good experiments, that plays a role, and there you have really real money incentives, because otherwise people may pretend they are nicer and more pro-social than they are in fact. Now, it's quite clear that the experiments on such surrogate system could easily be criticized for not producing robust information about reality, meaning that the results were also externally valid. In such experiments, there is no really genuine interest in itself in internal validity, namely the function of the surrogate system. Internal validity is only a means to hopefully achieve external validity, and this is, of course, the critical point of these experiments. Now, a sort of experiment that is even further removed from reality are so-called computer experiments. And computer experiments are in fact model calculations. And when you speak about or investigate what's the subject matter, then it's clearly that the real system is replaced by a mathematical model of that system. The object of the experiment is therefore not the system, but a computer representation of the intended system. And here comes in a fundamental difference of that kind of experiment with real experiments, real meaning on systems of the real world and not of a computer world, computer representations. The fundamental difference of that kind of experiment is that it can only make explicit what one has put oneself into the model. So it's only the model that reacts and does something. The real object cannot, to say it metaphorically, cannot make itself heard or show its resistance against the theorizing, which is the case in real experiments, because then the real system, or surrogate of the real system, can, so to speak, protest against what you are assuming about it by giving you results that are not consistent with your theorizing. That may happen, of course, in computer experiments as well, if you haven't thought through what you think of the system. And this is, of course, one of the aims of computer experiments, that they make explicit what you put into the system. But certainly, it's a different sort of resistance you get from the experiment than from a real experiment, and therefore this is further removed from reality. Now, as I said before, the latter, namely the resistance of the system itself against your theorizing, is fundamental for experiments. This is why you get information about the real world from experiments on real system in the stricter sense, and you do not get that by a computer experiment. Therefore, I think that computer experiments can never be a full surrogate for real system, for the real experiments, although we do not have anything else, for instance, in climate science, or almost nothing in climate science, because the real experiments on the climate as a whole, in the sense of getting information about it, are certainly not experiments. We can use historical data, but therefore we do have rely on computer simulations, and that is a problem. And of course, everyone working in that area knows it. And one should just be aware that computer experiments are just a different kind of experiment than real experiments. And sometimes people speak, especially in the biomedical sciences, when they contrast computer experiments with in vitro and in vivo experiments, then they are sometimes called in silico experiments because of the silicium material that's built up, that transistors are built up by. Okay. The fundamental question of computer experiments and in economic models more generally is, of course, external validity. What do I learn from a computer experiment about reality? How is that possible? How does it work? How does the knowledge from a computer experiment transfer from the model to the real world? I've treated that difficult question in section 6, and the answers to that question, the literature quite controversially, including my own theory on that transfer. And finally, I should come to thought experiments. And thought experiments are even further removed from reality. Some of them are very famous in physics and in philosophy, and they can make explicit implications of certain assumptions or theories, implications that become explicit by really thinking about certain situations, and you don't even need a computer. And to show you that is also relevant, I'm sorry, the object of the experiment is therefore a mental representation of the system of interest, not even a computer representation, but a mental representation of some system. And that mental representation is then investigated by some theory. And I give you a very short, very quickly an example from physics, but it's interesting. You may have heard of it. That's a very famous example from physics, carried out a thought experiment by Albert Einstein in 1907. And he said, imagine you are in an elevator that moves upwards with constant acceleration. So you're not moving with a constant speed, but the speed is increasing all the time, and the acceleration that's relevant here is constant. And then Einstein asked the following question, because then you get a force of inertia, because objects in that accelerator are inert, and because the elevator is accelerated, you feel the inertia, and then due to this inertia, you feel that on the bodies inside of the lift. And the question that Einstein asked, is that resulting force of inertia on the bodies inside the lift physically distinguishable from the force of a homogeneous gravitational field? In other words, when you put a system either, say, in that lift with constant acceleration, or you put it into a homogeneous gravitational field, can you by any sort of physical experiment and reasoning distinguish whether you're sitting in an elevator with acceleration, or are you sitting in a homogeneous field? And the answer was by Einstein, no, there is absolutely no way to distinguish these two situations that seem to be so fundamentally different. And that is then, of course, the suggestion that one could think about the possibility that these two seemingly so fundamentally different forces, inertia and gravitation, that they are in fact on a deeper level identical. And this was, by the way, this was one of the starting points of general relativity theory that suggests that gravitation is not a force by itself, a genuine force, but it's something else. It's a apparent force only. Anyway, thought experiments are, or at least were, also used in behavioral economics, and this is therefore important in our context. For instance, the evidentiary basis of Richard Thaler's papers in the 1980s on mental accounting, they were then criticized as Agner and Lowenstein put it. They were consisting of thought experiments. There were hypothetical cases of economic behavior patterns that were inconsistent with standard economic theory, and they were intended to have face plausibility to the reader. But they were pure thought experiments. And then you must ask the question as a critical economist, is that result of your thought experiment really an indicator that in the real world things behave similarly? And this is how Richard Thaler's early papers on mental accounting were indeed criticized. Now, in general, you can say from the early days of experimental economics to today, such thought experiments were increasingly criticized and replaced by experiments with less distance to reality, so with real choices, not imagined choices, and then with choices with incentives, with real money, for instance, and then even with people, not only students, but really people working and living in the relevant economic environment. Now, this was the first classification according to the distance of the experiments to reality. The second classification concerns the question whether an experiment is performed together with what is called a control experiment. Together, this pair of experiments is then often called controlled experiment. Now, the idea of controlled experiments was already described by John Stuart Mill in 1843, which is quite amazing how old it is, and it was called the method of difference. It is today, this method of difference, the absolutely standard procedure in medicine, and there the most common name is RCT, standing for randomized controlled trial. That terminology is also sometimes used in economics. It is necessary, this sort of procedure in medicine is necessary to identify the causal efficacy of a treatment, be it the causal efficacy of the treatment at all, or the causal efficacy in comparison to other treatments. Now, the basic idea is this. We have a random division of patients into one group, which is called the treatment group, and that gets the treatment, and a second group, which is called the control group. And the control group gets no treatment or gets a placebo. A placebo being something that looks like medication but has no content of that kind. So this is the simplest case of RCTs, where you have the treatment group and the placebo group or control group. And then the point is that if you find differences in these groups, then these differences can be ascribed to the causal effect of the treatment. Of course, a condition, a necessary condition for that to work is that indeed the two groups are in some sense identical or equal, and this is why the random division takes place. You say that statistically these two groups are equally composed, and therefore all the differences that we find between the treatment group and the control group are due to the treatment. And this is then the gold standard in medicine, and also, I come to it in a second, partly in economics, to identify the causal efficacy of treatments. As I said, that's the simplest case, but that's the basic idea, and the basic idea is what you should understand. Now, in economics, random controlled trials have become especially important in field experiments in developmental economics, as indicated by the 2019 Nobel in Economics that I mentioned already. Like in medicine, it's also possible to compare the efficiency of different measures that you use as treatments. And for instance, here's a question, again, somewhat simplified from economics. For instance, you have low school attendance in a certain area. And then the question is, how can we improve school attendance most in that region? And we have three different possibilities. One is giving the pupils free lunch. The second one is teaching them in smaller classes, or what is important in some regions of Africa, deworming. And then what you do is you assign pupils randomly to 4 groups, namely the 3 treatment groups with the different treatments and 1 control group, and then compare the results. And it turns out, and this is not to be found out differently, I think the only way to do that is by doing such a randomized controlled trial. Deworming proved to be most effective, with additional, by the way, positive side effects that were discovered in this study. So this is a very important experimental procedure, very important in many areas of science, medicine, biology, and now also in economics. Here's the third classification. Experiments differ from each other by different purposes. And there are 2 principal purposes. Again, I'm idealizing a little to get the essential properties. There are 2 principal purposes, namely, and this is better known, usually also in philosophy of science, experiments in order to test a hypothesis. This is what people are familiar with. This belongs, so to speak, to the stereotypes. Experiments test hypotheses. And the simplest case is you have a hypothesis that says there's a functional dependence of y on x. So y is a function of x. And then what you do in the experiment is you produce different values of x, and then you measure y, and then you look whether the function that you think it is the right one really measures up to these experimental values. If you calculate y on the basis of f, then you compare that with the measured values of y, and if there's too much difference, you say, no, it's been falsified. Now, many experiments in economics are of that test type. They are the best known. However, one should not overlook another kind of experiments that are experiments in order to explore certain phenomena. And that is a sort of controlled observation. And the main idea is also common in economics. For instance, in neuroeconomics or auction theory, what you do sometimes there is you run an experiment in order to explore what is going to happen if you make measure A or measure B. So for instance, in neuroeconomics, you do not know how the brain reacts to certain stimuli in a certain economic choice situation, and then you run an experiment in order to find out what is happening there. Even among these exploratory experiments, there are two principal kinds. And the first kind is when you know very little about the system in question. And then what you do is you intervene on the system in various ways. Scientists very often speak then about playing around with the system, and you observe how the system is reacting. That's one kind where you just try to find out, to understand somehow what the system is doing when you put different stimuli on it. The other kind of exploratory experiments is when certain quantitative aspects of some phenomenon are not sufficiently known. And what you do then is you change systematically certain parameters and observe the effect on the phenomenon, of course, mostly quantitatively. These are really two different kinds of explorative experiments, and the proportion of these kinds of experiments is very different in different disciplines. So for instance, in high energy physics, you do usually not run an experiment just exploratory in an explorative way without knowing anything about the phenomenon. Why? Because experimenting in high energy physics is extremely expensive. So you better know what you are doing. In physiology, by contrast, it's often the case that you have a certain physiological situation, for instance, how nerve cells grow in a certain situation, and you don't know very much about it. And then what you do is you run an explorative experiment in which you try out, for instance, different chemicals and look what the system is doing in reaction to your intervention. Now, here's my fourth classification, and that's also a very important one also for economics. It's the difference between intended versus so-called natural experiments. Now, so far, the experiments I discussed were intended actions by experimenters in order to find something out, be it explorative or be it with a testing purpose. But the funny thing is that sometimes a situation arises that is as if someone had arranged an experiment, and that is called a natural experiment. Now, natural means here, one has to be careful, the purpose of the arrangement, if there is any purpose of the arrangement, was not to carry out an experiment in order to gain knowledge. So we have a certain situation or arrangement that just happens for some reason, and we can read that sort of arrangement as if it was an experiment, and therefore we can interpret the results as if it was an intended experiment. Now, here's an interesting example, first one from the natural sciences. You know that there are nuclear reactors to produce energy, electrical energy in the end. And it was found that there was a natural nuclear fission reactor in Africa at some place, where by natural processes, there was a uranium deposit that was enriched enough that a self-sustaining nuclear chain reaction happened. That happened in Gabon, in Africa. So that was a sort of natural nuclear fission reactor, and that was very interesting because that was running for a long time, a couple of 100,000 years, and then one could see what happened to the results, to the end products and side products of the fission, and it was an interesting natural experiment. Now, in economics, we do have the same sort of situation. That means there are processes happening not intended as experiments in order to find something out, but they were either historically just happening or they were intended but for different purposes. And here's the first example from economics that is discussed in what is called the new minimum wage research. And that is You just investigate real cases of minimum wage increase in some county or state and its employment effect for low wage workers. You know that there is the theory that minimum wage is an intervention into a market with disastrous effects, because the fear is that if you introduce minimum wage, then you get a higher percentage of unemployment in the low wage sector, labor sector. And so what you do is you investigate those real cases, and there are even something like control experiments. Namely, sometimes it happens that the development of employment in neighboring county or state you can observe where no minimum wage increase was introduced. And that situation happened again and again in the United States. And then you could compare the two, and the county without minimum wage increase could then be compared with a county with minimum wage increase, and you could see, if the counties were comparable, what the effect of minimum wage increase was. And interestingly, the result was from a publication that you can find here. The result was that the evidence points to little or no employment response to a modest increase in the minimum wage. This is in a publication from Schmidt, 2013. Why does the minimum wage have no discernible effect on employment? From the Center for Economic and Policy Research. And here you find the web page where you find that. So that's an interesting case of a quasi-experimental investigation. You find, of course, many of those cases, similar cases, in the history of economics area. Here is a second example from economics, also an interesting one. And I use this example very often to tell people who do not know much about economics what modern economics investigates, because it's something which most people outside of economics have no idea that economics investigates. And this is a publication that asks, here's a sentence from the abstract: we estimate the impact on pilgrims of performing the Hajj pilgrimage to Mecca. You know that the Muslims have once in their life to travel to Mecca to make this pilgrimage, which is called the Hajj pilgrimage. And the question is, these people asked there in this investigation whether that pilgrimage has an effect on the pilgrims. And the method they are using, our method, compares successful and unsuccessful applicants in a lottery used by Pakistan to allocate Hajj visas. Excuse me. The point was that there were not enough places to travel to Mecca, and then the Pakistani administration used a random distribution of people who were able then to travel to Mecca and others who weren't. And economists saw that and saw that this is a naturally occurring experiment. And then we can, if we compare these two groups, we can measure what sort of impact the pilgrimage to Mecca had on its participants. And this was published, Klinging-Smith, Kaiwa, and Kramer, estimating the impact of the Hajj, religion and tolerance in Islam's global gathering. The question was there, does it have an impact on radicalization of Muslims? And it was published in the Quarterly Journal of Economics. You know, this is one of the absolute top journals in economics. So this is an example how this kind of natural experiments now finds attention in the very, very best journals in economics. And now finally, the fifth classification of experiments is sometimes people speak literally and sometimes metaphorically about experiments. And in the literal sense that we have seen, I think an experiment has an epistemic purpose. You do something, an intervention, in order to find something out, what you don't know or are not sure about. So it's quite clear it's a sort of action that has an epistemic purpose. And this is what in the literal sense an experiment is. In the metaphorical sense, people also sometimes speak about experiments, but then they only speak metaphorically about it when the thing that is happening there is not really intended as something that produces knowledge or information, but something of which the consequences are unsure. Then we also speak in normal language about experiments. So here's an example. That was in Germany in 2014 when a general minimum wage was introduced. And then some people spoke about that they said, this is an experiment. In the sense that one didn't really know what the effects were going to be, and people believed they were potentially dangerous, and then they called it, what Germany is doing here is an experiment. You find that, unfortunately, in German only. I did not find a better source here. But this is also when we speak about experiments in everyday language. But be careful, these are not experiments in the sense we use the term in science and in economics especially. And this is the end now of this section. I hope what you learned in this section was that indeed experiments play now a fundamental role in economics. The sense is that people in economics can find out things, especially causal relations, that you cannot find out without experiments, at least not in any sense of a good confirmation of your causal hypothesis. Thank you very much. And then comes the next section.